My name is John Gorman. I'm a technical program manager at Waymo. Chin just described how Waymo is advancing its ability to scale in the real world. And now we'd like to talk about how we're using that experience from our scale to also enable the broader AV community to engage in fundamental industry research areas and how you can get your hands on real world Waymo data for your research. In this session, we'll provide an overview of the various Waymo open data sets and our benchmarks. And we'll also introduce the latest updates from 2025 and dive into each of the challenges from this year. We've invited some of our top performing teams from the challenges to present alongside us on their methods. So the journey to fully autonomous driving is a story of shared innovation, and we are deeply aware that we stand on the shoulders of giants. Decades of foundational research in computer science and machine learning have paved the way from what we do today. And that is why we are proud to offer the Waymo Open Dataset, which is one of the most comprehensive and diverse collections of autonomous driving data to give back to the research community and continue to drive innovation in this space. We started with our perception dataset, which we first released back in 2019. It contains data that's suited for perception tasks, like detection, tracking, and segmentation. The initial release for our motion dataset was in 2021. It's a relatively large dataset suited for prediction, planning, and simulation tasks. We continue to make incremental improvements on these datasets. 2025 was a big year for us. Alongside hosting our 6th annual Open Dataset Challenges, we released a neat end-to-end driving dataset, which contains camera data that is particularly suited for fine-tuning vision-based planning models on long-tail scenarios, similar to what Chen just featured in her presentation. And we'll provide more information on that in just a minute. Since we've launched the Open Dataset, 53,000 researchers have used it as a high-quality tool to explore topics in autonomous vehicles, robotics, computer vision, and other machine learning more broadly. And in the last 6 years, there have been 4,000 academic papers published either citing the open data set or using it as a benchmark for their research. And speaking of benchmarks, we maintain the most comprehensive set of benchmarks for various tasks relevant to the autonomous vehicle research community. Based on our perception data set, we have benchmarks covering various detection, tracking, segmentation, and pose estimation tasks. And based on our motion data set, we have various prediction and simulation benchmarks. This year, we added 2 new benchmarks, the scenario generation and vision-based end-to-end driving, which leverages our new end-to-end driving data set. And my colleagues will discuss these new benchmarks in greater detail later. So this here, our 6th annual round of challenges, we featured 2 new challenges based on those benchmarks. And we also like to rerun challenges from previous years to observe improvements and approaches from the community. And this year we ran our interaction prediction challenge for the first time since 2021, and our sim agents challenge for the 3rd year in a row. And lastly, before we dive into the challenges, we're very proud of the engagement that we got this year. We've had a total of 128 teams participate in the challenges, which is about a 34% increase from last year. We had 935 total submissions, which was another 30% increase from last year. And we had 70 leaderboard submissions across the 4 challenges, which is over 50% more from last year. And lastly, while we don't collect detailed demographic data from everyone who submits to our benchmarks, just within our community of potential finalists, we had over 10 countries represented. Okay, now I'll turn it over to Wensheng to discuss our new end-to-end data set and challenge.
Yes, thank you, John. Hello, everyone. I'm Wensheng, research science and Waymo. So let's talk about our new challenge this year, the vision-based end-to-end driving challenge. So what is this challenge about? Our traditional AV stack, we already have perception, localization, prediction planning module with different sensor modality like LiDAR, radar, camera. But in this challenge, we ask the participants only use cameras and ego states and approach the future weapons directly. So why does this topic was exploration? First, it has really good scalability. You just drive around city with camera, with GPS, and then you collect the data. There's no hidden annotation needed, right? Second, it has a natural synergy between the multimodal large language models and entering driving. There are a lot of research has shown like by leveraging the more knowledge of MLMs, we can solve these long-tail scenarios in entering driving. So to do end-to-end driving research, we need a good benchmark. But the current existing benchmark, academic benchmark, are usually too simple. Like Dataset using or CVPR'25, they are really just have nominal data sets. But what we really want is some long-tail data set, as Chen mentioned before. And also, we need a good new ER metric. So AD is definitely not good enough. And next thing is good, but it requires the object annotation. For long-term scenarios, they usually has some real objects, which is hard to annotate. So that's why we launched this challenge to fill these two gaps. So in this challenge, we launched a new exciting data set that is featured 12 hours of ultra-rare driving scenes, capturing scenarios that occur with less than 0.003 percentage frequency in daily driving. What does that number mean? That means you may not even see one of the scenarios in your whole life during your driving. So let's take a look at some examples. First, you can see birds flying, but have you seen a flock of angry birds rush to you during driving? You may see deers cross the road, but how about 3 deers in a row at night and his residence area? This is super rare. And this is a safety critical scenario. A scooter is falling down, and we build a nest serve to save her life. More than say like AI can save people's life. Now it's a time to test the algorithm. And this one is super complex. So this is a marathon. You see a lot of traffic cones. You saw people doing marathon, and the traffic light is right. And the traffic man asks you to go through actually. So this will be very confusing for any AV system. And this is another simply critical one. There's a vehicle here doing very aggressive cutting, and you need to respond correctly to avoid any collisions. Here's a life or death scenario. There's oncoming vehicle in the same lane in the opposite direction with very fast speed. And then there's a police car is chasing it. So I think this is something you can only imagine in a movie, but here's it. So as you can see, all these 6 videos are super rare. But we have 4,000 such videos in this release. And we have 3 different sets, training, validation, and testing sets. For training and validation, we have 20-second videos with driving logs. And for the testing sets, we only release 12 videos. And we ask the participant to predict the future 5-second waypoints based on the last frame. And for our data, we have 8 camera surrounding vehicle released. We have ego states. We have high-level comment routing. And for the validation, we also released a new label, the RFS label, which is called Richer Feedback Score. So for all the videos, we ask human labelers to label 3 diverse trajectories with a score from 0 to 10. 0 means this is super dangerous trajectory, don't go like that. And 10 means this is good trajectory to go. And then we will compare the prediction with these 3 trajectories to match the distribution and then get a final score. So before I delve into the final list of the winners, I want to say like we really appreciate every participant joining this challenge. A lot of interest master we have seen, it's really insightful. And so our winner is Yuri Pan from EPFL. And second place is Diffusion LTF, which is from University of Tübingen and ASMT and NVIDIA Research. And third place is Swing Trajectory from Hanyang University and Reflux Inc. And we also have a special mention, Poutine, which achieved very, very high score in the report. and from Mela Kubik AI Institute, and I will leave the stage for Poutine to present.
Hi, so we'll be presenting Poutine. We wanted to thank Waymo for this special mention, even though we weren't able to compete due to being from Quebec. This is joint work with Rod and I, as well as our co-authors at the Mila Quebec AI Institute. So what is Poutine? Poutine is a vision language model for long-tail driving. So we trained this vision language model using a larger training corpora than was provided by the Waymo end-to-end training dataset. Specifically, we additionally added this co-VOA dataset, which consists of 83 hours of front view driving in Japan. And to align to the vision language model's language space, we automatically collected language annotations using a large Quen 72B vision language model. And we specifically instructed the model to output annotations in the following format shown on the right, where it outputs a critical objects list, as well as an explanation and meta behavior that describes the optimal future driving trajectory of the ego. And we followed a simple two-stage training recipe built on top of the Quen 2.5 Vision Language 3B model. So the first stage is what we call Vision Language Trajectory Pre-training, and this gets us our Poutine base model. And this is just standard next token prediction on interleaved vision language and trajectory tokens. And interestingly, we only required the front three views of the present frame to achieve strong performance. And the second stage gets us our final Poutine model, and this is with RL preference fine-tuning using the GRPO algorithm. And this was fine-tuned on the provided Waymo validation dataset, where we used RFS directly as a reward signal, and we also had an additional format reward for formatting the trajectory properly. So how does Poutine perform? So at the end of the submission deadline, Poutine significantly outperformed the other submissions, with the model before RL still outperforming the other submissions by a considerable margin.
Several experiments that we conducted as part of the challenge. We did our evaluations on the Waymo validation set. So here we show some comparisons between different pre-training and inference strategies. So the first two columns with which of the driving data sets were used during pre-training, either the CommULA or the Waymo end-to-end driving data set. And then the next two columns specifies whether we used generated language annotations during pre-training and whether we did the chain of thought prompting at inference time. So the first interesting result that we found is that we already get pretty good score on the Waymo driving dataset when we only do training on the CommULA Japanese driving dataset. So this is without seeing any Waymo data during training. And the next two rows, these are experiments that basically showed that both the generated language annotations and the COVID driving dataset used during training gave us overall the best score when we did evaluation on the Waymo driving dataset. And then finally, the last interesting result that we show here is that when you do chain of thought at inference time, we didn't actually see an improvement in performance, which is consistent with other works that have shown this in the past, and indicates that this is still an open area of research. Next, we'll evaluate the impact of our second stage reinforcement learning as part of the Poutine pipeline. So for these experiments, we trained on 90% of the scenarios in the Waymo validation set, and then we did our evaluation on the held out test set, where we show the results in this figure here. So from this figure, we can clearly see that our second stage clearly yields strong gains when we do reinforcement learning on our Poutine-based model. And the second result that we show here is that when we look at a model that was trained on both the CodeLang and the Waymo driving dataset, and the model that was only trained on the Waymo dataset, we see that the model that was trained on both driving data set gives us an overall better performance when we do our second stage reinforcement learning stage. And as a final part of our results, we'll show 3 example scenarios where we plot our model predictions shown in green, and you can see compared to the future trajectory of the eco shown in red. So in this example, we see that there's a vehicle that emerged onto a lane from the right, and our model successfully slows down. And this last example, there's an animal that crosses the road, and the model predicts to slow down.
So what are the main takeaways of Poutine? So first is that you can take these public pre-trained vision language models without modification, and they can serve as very powerful general architectures for vision tasks such as end-to-end planning, even if you're not explicitly using language as a modality. We also show that a very simple training recipe of next token prediction pre-training, followed by lightweight RL reference fine-tuning, can yield state-of-the-art planning results on this benchmark. And finally, Poutine requires very minimal human effort, in that no human labor was required to train the Poutine-based model, and reinforcement learning only required around 500 frames of preference-labeled trajectories. Thank you very much.
All right, so now we're going to show a video from the Diffusion LTF team, which was our second place finisher in the Indian driving challenge.
Hi everyone, I'm Kashyap. I'm excited to present our solution to the Waymo end-to-end challenge. The AV datasets available to the community today are extremely complementary. On one hand, you have synthetic datasets like Carla that have really precise and diverse annotations, but lack diversity in scenarios and have visual domain gaps to real data. Then we have perception-centric datasets, which have 3D annotations and maps, like the Waymo Open Perception Split or NavSim, where you can learn perception tasks very well, but the data is not curated for extremely challenging scenarios. And you have, on the other hand, the data that was released for this challenge, where there is no annotation, making it extremely difficult to learn models on this data. But the scenarios are really challenging with lots of rare and infrequent events. So our approach is to try to unify all of these data sets into a standardized format for training. We do this in a repository which we call OpenXAV. And one of our goals is to have a simple format that's easily extensible so that we can add other public data sets into this mix for future work. With this repository, we have a multi-stage training pipeline where we pre-train on most of the perception-centric data, where we spend the large portion of our training budget learning tasks like 3D detection, bird's eye view segmentation, and depth estimation. Here, the planning heads or planning task is not trained, and the network focuses on learning good visual representations. After this, we have a very lightweight post training phase where we fine tune the entire model end to end on the challenging scenarios in the Waymo end-to-end split used in the challenge. So our architecture is based on latent transfuser or LTF, which is a well-established backbone on NavSim and Carla. The main chunk of the architecture is a perception encoder that takes three front viewing cameras as input and generates bird's eye view scene tokens. It also encodes the ego status like the velocity and navigation command, and all of these tokens are concatenated together. Now, the standard latent transfuser planning head predicts the waypoints deterministically from these tokens, but our architectural innovation for this challenge was a diffusion based addition to the latent transfuser architecture. Specifically, we have multiple modes of noisy trajectories, which through a trajectory encoder, which is a self-attention module, are encoded to waypoint queries. And these entire set of status and BAV tokens are used with a transformer decoder to decode these queries into denoised predictions using a standard DDIM formulation and scores for classifying which mode is most suitable for this scenario with a cross entropy loss. So our final architecture for the challenge actually used a common backbone encoder and two parallel planning heads, both the deterministic latent transfuser and our new diffusion LTF head. And as per the main challenge metric, though both heads independently achieved similar scores, we see that ensembling the predictions of the two heads together gives a boost, which is further increased by drawing more samples from the diffusion decoder. Additionally, we find that pre-training is crucial. So pre-training on any one of the data sets already gives a large boost in performance compared to not pre-training. And in particular, the Waymo open perception split is well suited for pre-training in this challenge. So here are some qualitative results of our method. As you can see, it can handle pretty complicated scenarios in the data set quite well. So this is it from my end. Thank you for listening.
Okay, so before we talk about the rest of the challenges, I want to provide an overview of our perception and motion data sets. The perception data set is comprised primarily of LiDAR and camera sensor data. We also provide labels for various training tasks, including 2D and 3D bounding boxes, key points, and various forms of segmentation. We also provide mapping data in the form of a 3D road graph that you can use to align sensor data with road features. And another feature of the data set is object assets, which are accurately correlated camera and LiDAR observations on a large collection of vehicles and pedestrians. The data set is provided in a modular format, so you can download and work with all the portions that you need. And as I mentioned, the motion data set is suited for prediction and scenario simulation tasks. It features a much larger number of scenes with over 570 hours of driving data collected from over 100,000 driving scenes in 6 US cities. We also provide accompanying bounding boxes produced by an off-grid model and 3D mapping data. Over the last couple of years, we added LiDAR data and camera embeddings to encourage more end-to-end methods. And later this year, we plan to release an update with route information for the Ego vehicle. This is in support of one of our most popular feature requests for Waymax, our Waymax simulator. More on that shortly, to enable new metrics like route progress ratios. Okay, now cutting our second challenge this year, the interaction prediction challenge. This is our second time running this challenge. First time was in 2021. The objective for this challenge is to predict the joint future positions of Tim interacting agents for 8 seconds into the future, given the agent's tracks for the past 1 second on a corresponding map. This challenge adds the additional requirement over traditional motion prediction benchmarks that participants must jointly predict the behavior of multiple agents. Here we have an example from the training data set where there are 2 vehicles making unprotected left turns, where both of them need to wait for the other vehicle before proceeding. The task is to use the first 1 second of this data as agent history, and then predict the trajectories of the interacting agents for the remaining 8 seconds. All right, and the challenge is to, jointly predict the trajectories and their confidences for the 2 given agents in the scene. Up to 6 trajectory pairs can be predicted per example. And so here you can see we have the 3 predicted trajectory pairs for the 2 vehicles. We updated our interaction prediction benchmark last year. So this is the first year for us running the challenge with soft mean average precision, or soft MAP, as the evaluation metric. The soft MAP design addresses the multimodal nature of trajectory forecasting. So here's how it works. First, we classify each ground truth trajectory into one of 8 behavior buckets, such as left turn or right turn, and one of 3 object type buckets. And then next, we evaluate the model's predictions. And prediction is considered a true positive if its path is within a certain tolerance of the ground truth. These tolerance thresholds are dynamic. They scale with both time and the object speed to account for increasing uncertainty. The soft component of the metric is crucial. It does not penalize the model for generating multiple valid predictions for a single agent. This intentionally rewards models that can capture the inherent uncertainty in a traffic scene, where several future paths may be plausible. And finally, the overall performance is quantified by computing the mean average precision over all the behavior and object buckets. This aggregation gives us a single robust score that reflects the model's overall predictive capability. So it's my privilege to announce the winning teams from this year's Interaction Prediction Challenge. First, I want to thank all the participants in this year's challenge. We had some really strong participants, and we appreciate all the hard work that went into it. Third place team with method name B-Top Ensemble achieved a soft MAP score of 0.2573, and our fifth place team, Retro Motion, achieved a very close score of 0.2562, which earned them as an honorable mention for the challenge. And I think Raiden from the Retro Motion team is actually here with us. All right, and then in second place was the impact method. And in first place, the parallel ModeSeq, which achieved a very staggering 0.2978 score on our soft MAP metric. So we'll now hear from the parallel ModeSeq team on their method.
Hi everyone, I am Zhou. In this talk, let me introduce Parallel ModeSeq, our solution to the Waymo Interaction Prediction Challenge. Anticipating the multimodality of future events lays the foundation for safe autonomous driving. To this end, we need to capture the full distribution of agents' future. However, only one possibility can be observed in real-world driving data, which makes multimodal behavior prediction challenging. Our framework for multi-agent behavior prediction comprises a scene encoder and a trajectory decoder, which encodes robust traffic scene representation efficiently and decodes multi-agent trajectories in consideration of multimodality and scene consistency. We adopt the query-centric encoder proposed in our work QCNet, which encodes viewpoint invariance input embeddings and relative spatial temporal position embeddings, fusing the scene context using relative position-based transformers. To learn multimodal behavior of agents, most prior works adopt the paradigm of set prediction, where the modes are unaware of each other or their relationships are weakly modeled. Moreover, these methods employ the winner-take-all training strategy, suffering from limited trajectory diversity and uncalibrated mode confidence. As a remedy, some recent works opt for dense mode prediction followed by heuristic mode selection. Despite their improved trajectory diversity, they often produce low-quality trajectories. In particular, the anchor-based approaches under this paradigm fail to scale for joint multi-agent prediction, since the combination of dense anchors from multiple agents is exponential. In contrast, our work ModeSeq published in this year's CVPR models modes as sequence, which captures the relationships between modes by reasoning about the next mode step by step, conditioned on the previous modes. This method has improved trajectory diversity, calibrating mode confidence, and good trajectory accuracy under the paradigm of sparse mode prediction. However, ModeSeq relies on recurrent mode generation, which is too slow for real-time prediction. For this reason, we developed a parallel version of ModeSeq. In parallel ModeSeq, we translate the mode set into a sequence via causal mode-to-mode attention, and then leverage Transformer's capability of parallel decoding to predict almost in parallel. We also stack multiple layers and apply training losses to each layer for iterative refinement. In between decoding layers, we employ an operation of mode rearrangement to prioritize the refinement of the more probable trajectories in the next layer. To perform multi-agent joint prediction, we follow our work QCNext to add a future interaction transformer that can improve the scene consistency. Moreover, we achieve scene-level mode scoring via max pooling over all target agents embeddings in the scene. As for training, we propose the EMTA loss to replace the popular winner-take-all loss, in which we optimize the match mode decoding at the earliest step in the mode sequence. We found that our EMTA training strategy results in better mode coverage and confidence scoring without significantly sacrificing trajectory accuracy. The training loss consists of 3 parts, including the regression loss based on the Laplace negative log likelihood, the classification loss based on the binary focal loss, and the margin ranking loss aiming at minimizing the average number of confidence inversions in each training batch. Our model has 11.2 parameters. Without employing tricks like model ensembling or dense mode prediction followed by non-maximum suppression, parallel ModeSeq outperforms other submissions by a large margin, which demonstrates the advantages of our overall framework. To summarize, we create a new path to solving multimodal problems, including a mechanism of sequential multimodal decoding, an architecture of iterative refinement with mode rearrangement, and a training strategy of EMTA label assignment. Thank you for listening.
Thank you, John. I'm Reza Majurian from Waymo, and I'll be presenting the sim agents and scenario generation challenges and their results for this year. So before we dive in, we thank all the participating teams for all the great work and all the submissions that you've sent us. We rely on simulation for testing the autonomous vehicle software on diverse scenarios and rare scenarios that may not come up often in the real world. The Sim Agents framework gives us the ability to simulate these diverse scenarios and test the AV software. In this challenge, the inputs include agent history and scene data over 1 second, and the objective is to generate 32 realistic rollouts of the scene with 8-second future trajectories for all the agents. So the model sees where all the agents have been for the past 1 second, and then it comes up with new futures for these agents that are present in the scene. Next slide, please. To better motivate the Sim Agents challenge, we can take a look at a motion prediction model. This is a challenge that we have run for the past 4 years, but we're not running it this year. But if you look at such a model, this model predicts trajectories and associated scores for each agent. These predictions can be used by the onboard software to create a motion plan for the autonomous vehicle, but it cannot be used for simulation. If we just sample from these predicted trajectories, we might end up with agent behaviors which are not mutually consistent, and that will not yield a realistic scenario. We just saw how the interaction prediction challenge focuses on this problem by expecting consistent trajectory sets from a pair of agents. The Sim Agents challenge takes this to the next level by requiring a set of consistent trajectories for all the agents in the scene. Next slide, please. So we evaluate the submissions by compiling a distribution of simulated behaviors for each agent and then comparing those distributions with the ground truth behavior of that agent. For each agent, these distributions capture the agent's motion profile, how well it follows the map, and how it interacts with the other agents in the scene. The final metric is a weighted average of all the metrics in these 3 categories. Next slide, please. With that, I would like to introduce the winners. In first place, you see TrajTok from Shanghai Jiatang University. In second place, you see RLFD Sim from University of Alberta and York University. And in third place, we have Combot from Cognibit. An honorable mention goes to UniMM, that's short for Unified Mixture Model, from Zhejiang University and Horizon Robotics. Next, you'll hear a 5-minute video presentation from TrajTok.
Hello everyone, I'm Zhiyuan Zhang from the Think Lab of the Shanghai Jiao Tong University. In this talk, I will introduce TrajTok, a trajectory tokenizer for discrete token prediction-based behavioral generation models. Behavior generation is an important component of autonomous driving simulators. Recently, inspired by large language models, a series of behavior generation models adopt the next token prediction (NTP) paradigm, such as TrajTok and SMART. This model tokenizes agent TrajTok of a certain interval into discrete tokens and predict probabilities for each token. Then select the best TrajTok token for the next interval. There are two types of TrajTok tokenizers in NTP behavior generation models: the data-driven methods and the rule-based methods. The data-driven methods process TrajTok in real world with classical or other algorithms, such as the k-disks. Rule-based methods directly generate the vocabulary without the data. In this work, we conduct an analysis of what makes a good TrajTok tokenizer in behavior generation and propose the TrajTok tokenizer. This figure shows the trajectory vocabulary generated by the k-disk tokenizer and our TrajTok tokenizer. Each color line represents a trajectory token with 0.5 seconds in agent-centric coordinate system. The token generated by k-disks is asymmetric and there are some batch trajectories, while the tokens generated by TrajTok is symmetric and has a high quality. In the top right image, orange dots indicates the endpoints of the tokens, and the blue dots indicate the endpoints of real trajectories in the dataset. Compared to k-disks, TrajTok has a wider coverage. TrajTok generates the token with 4 steps. First, we extract all valid trajectories of a certain length in the dataset and normalize to the agent-centric coordinate system. The trajectories are copied and flipped along the x-axis to ensure symmetry. Second, we generate the grid with a predefined range and interval. Each trajectory is associated with a cell. If its endpoint found with the cell with trajectories associated is colored in orange in this figure. We can see that there are some abnormal points far away and some holes. Third, for each cell, we compute the numbers of cells with trajectories around it with a binary map. In this way, we filter the abnormal points for the holes and expand the border. Finally, we generate a trajectory token for each valid cell. If there are trajectories associated with the cell, the token is generated as an average. If not, we generate the token with the curve interpolation. The generated trajectory vocabulary can be used in various NTP behavior generation models. We also improve the token-related designs. We propose a special aware label smoothing method for cross-entropy loss used in the NTP behavior generation model. Standard label smoothing assigns a sub-target probability to each non-ground-truth token, while we assign a larger probability to tokens that are specially close to the ground truth and give a smaller value to tokens that are far away. This special aware label smoothing can both reduce the errors and improve generalization. We use the Smart Tiny model as a base NTP behavior generation model. We replace the k-disk tokenizer with TrajTok and use a special aware label smoothing method for loss. Compared with the baseline, our method greatly improves the performance and ranks second on the leaderboard. In this study, we found that a good trajectory tokenizer should be well in coverage utilization balance, symmetry, and robustness. For coverage and utilization, the tokenizer should cover trajectories that do not appear in the dataset but may occur in reality, and avoid including too much invalid trajectories. For symmetry, considering the symmetry of vehicle kinetic models, the diversity of real-world traffic scenarios, and the left-hand and right-hand traffic routes in different regions, generally the possible ratio of the trajectories is symmetric. For robustness, that one answer should not be easily influenced by noise in the dataset. You can find more information in our technical report. Thank you for listening.
Thank you to the TrajTok team. We also have an update to share on Waymax, which is a lightweight research simulator developed by Waymo for solving sim agents and planning problems. Waymax is written entirely in JAX, so it's differentiable and hardware accelerated. The code base was recently updated and you can check it out on GitHub. Next slide, please. Next, you'll see an overview and the results from the Scenario Generation Challenge, which is a new challenge introduced this year on the Waymo Open Motion Dataset. So this challenge extends the Sim Agents Challenge, which we just saw. In that challenge, all the agents are given and only their futures are generated by the models. In the Scenario Generation Challenge, there are no input agents. All the agents besides the AV are generated by the models. The only inputs to the model are the scene map and a 1-second history for the ego vehicle. The model is also told how many agents to generate for each type. For example, a scenario might ask for 15 vehicles, 8 pedestrians, and 1 cyclist. The models are then expected to generate 32 full instantiations of the scenario, which requires generating initial agent positions, bounding box dimensions, and full 9-second trajectories for the requested agents. So the outcome is that you have created a stronger tool for generating diverse driving scenarios, and this can better test the AV software in novel situations. The scenario generation metrics are also an extension of the Sim Agents metrics. In the Sim Agents challenge, behavior profiles are created and scored for individual agents, but in this challenge, we generate and score collective distributions from all the agents present in the scenario. And we compare that with the ground truth. With that, I would like to introduce and congratulate all the winners in the first round of this challenge. The winners are SimFormer from Shenzhen Urban Transport Planning Center, UniTSG from Tongji University, Yanshan University, and Xi'an Technological University. And in third place, you see Shred from University of Tübingen and NVIDIA Research. Lastly, honorable mention goes to InfGen from UCLA. You can check out the tech reports from all the winning teams for all the challenges on the workshop website. Next, you'll see a short video by the winning team, SimFormer.
Hello everyone, and thank you for being here. I'm Sun Wang, and today I'm excited to share with you SimFormer, the system that earned first place in the Waymo Open Scenario Generation Challenge 2025. Let's dive into how we achieved this milestone. Rule-based and simulator methods like Sumo and Carla rely on predefined traffic rules or microscopic simulation engines to synthesize scenarios, which result in lacking of realism and diversity, especially for rare events. On the other hand, regression-based approaches model agent positions, attributes, and trajectories as continuous variables, typically regressing to real-world distributions using neural networks. While effective for basic realism, such models face challenges in diversity, scalability, and efficient generalization. Recently, discrete tokenization and autoregressive methods have shown strong promise. Inspired by language modeling, these approaches convert continuous scene elements and trajectories into discrete tokens and leverage GPT-style transformers to predict token sequences. This enables scalable, flexible, and generalizable multi-agent scenario synthesis. First of all, we come to the problem formulation. The inputs include a high-definition map segment, the 1-second history of the ego vehicle's motion, and the expected number of agents to generate for each type. Given that, it is to generate a set of non-ego agents and their full trajectories over a fixed time horizon time steps. Each agent is characterized by its type, initial position, heading, and 3D bounding box dimensions. A trajectory is composed of center positions and heading angles over time. The number of generated agents per type must match the provided count. In SimFormer, This problem is approached by autoregressively generating discrete tokens that represent agent types, placements, attributes, and full trajectories, conditioned on the map context, ego history, target agent type counts. For the input preparation, we vectorize the map and extract relevant polyline and context features. This input is encoded into fixed-length token sequences to serve as the conditioning context. In the tokenization step, all agent-related elements, including initial positions, physical attributes, dynamic attributes, and trajectory fragments, are discretized into interpretable token vocabularies via clustering or binning techniques. Next, SimFormer iteratively generates agents in a grouped and type-aware manner. For each agent, it sequentially predicts an agent type token, a position token, attributes tokens, and a sequence of trajectory tokens. Finally, the generated tokens are mapped back to continuous representations, recovering full initial states and 91 time-step trajectories. These are then serialized into structured outputs for evaluation and submission. Dive into the tokenization strategies. There are 3 key points. For the initial position tokenization, we firstly represent each agent's location relative to the ego vehicle's local coordinate frame, to capture the spatial distribution of non-ego agents. And then we apply clustering to these relative positions across the training set to obtain a finite set of representative position tokens. Therefore, what the model predicts are the relative position distribution relative to the ego vehicle. This tokenization strategy allows flexible and scalable modeling of complex multi-agent spatial layouts. For the tokenization of physical and dynamic attributes, we discretize that into 2 separate joint token vocabulary to improve efficiency and capture correlations. The agent's length and width are jointly discretized. And the agent's initial speed and yaw angle are jointly discretized. Each size token corresponds to a bin in a tailor-dimensional space. Therefore, what the model predicts are probability distributions over these 2 attribute token vocabularies, which enables to cover the real-world agent attribute distributions. Finally, to efficiently represent agent motion, we follow SMART's approach by segmenting trajectories into fixed-length intervals and applying clustering to build a trajectory token vocabulary. Moreover, we employ a reverse matching strategy to ensure that the first token is physically consistent with the agent's given initial state. To summarize, here is an overview of the tokenization strategies. SimFormer constructs all token vocabularies from training data. Position tokens are obtained via clustering on ego-relative coordinates, while size and dynamic attributes are discretized through uniform binning. Trajectory tokens are derived from clustered motion fragments. We discretize the task by clustering trajectory data into 4 token types: position, size, dynamic, and trajectory, and employ a dual-stream transformer for prediction. The architecture consists of a 3-layer map encoder and a 6-layer token decoder, where map features are first processed through shared layers before autoregressively decoding agent tokens. Now, we will show the details of implementation. The left table is the configuration for training process. The right table shows the parameters for clustering and discretization algorithms. Here is the model result, following the official Scenario Generation Challenge 2025 data splits and evaluation protocols. Here is the method comparison result. SimFormer demonstrates superior realism and diversity across all key metrics. In conclusion, we presented the model named SimFormer. The technical innovations to highlight are well-architected tokenization strategies and a scalable autoregressive architecture. The experiments on the Waymo OpenMotion dataset show the model ability to capture the complexity and diversity of real-world traffic. Please allow me to introduce myself. I am Sun Wang, an AI engineer at Shenzhen Urban Transport Planning Center, specializing in 3D machine learning, computer vision, and multi-agent systems. At SUTPC, a global leader in smart mobility solutions, I focus on innovating intelligent transportation technologies. Feel free to connect via email or visit my GitHub to explore my work. Looking forward to exciting discussions.
So Tina published 16 technical reports from an incredible field of participants. On our website or the workshop on Cloud Strategy website. We encourage you to go and check them out. And lastly, I want to acknowledge the team that made these data sets and challenges possible this year. This year's release was the most ambitious yet. It's a large team of passionate engineers and researchers who look on this ambition to do out their duties to pull it off. That effort will only possible thanks to some contributions from teams all across Waymo.